Okay, so this video is going to be on acid strength in pKa, and remember the acid strength in pKa is basically how readily a compound can donate a proton. Okay, so we're going to go over a few things that we should already know from general chemistry, but again is really important for organic chemistry. So the more readily a compound gives up a proton, then the stronger that acid is. So let's take a look at HA plus water. Remember, this is an equilibrium arrow, and that goes to A minus plus H3O plus, right? Now, keeping with the theme of drawing the acid as blue and then the base is red, we've got the lone pair on that water attacking the proton on HA, and the two electrons in that HA bond going to A is the lone pair. Okay, now remember from general chemistry that we have KEQ, the equilibrium, is equal to the concentration of the products over the concentration of the reactants. Okay, and so up above we have the reactants on the left side and the products on the right side. Okay, now what does this look like when we have with the particular equation that we put up? Now that's the concentration of H3O plus times the concentration of A minus over the concentration of HA times the concentration of water. Water being a reactant. But we can simplify this, but it's now called Ka is equal to the concentration of H3O plus times A minus over the concentration of HA. So we basically omit water because it's there in abundance, and this is Ka is actually a good indicator on the strength of an acid. The stronger the acid, the larger the Ka. So that means that's because that acid gave up a proton to water and formed more H3O plus. Okay. Now what we typically use this for is if we apply it Ka to the negative log, then we can get something called a pKa. Now the smaller the pKa, the stronger the acid. So this is opposite, right? Notice the larger the Ka, the stronger the acid, but since it's the negative log of Ka is equal to the pKa, the smaller the pKa is, the stronger the acid, okay? So let's talk about some practice. Which compound in each pair is the stronger acid? Sorry. Which compound in each pair is the stronger acid? All right, so let's write a couple out, and then what you should do, as always, is pause the video, try the problem on your own, and then see how you do after I give you the answer. Okay, so we've got propane and ethanol. pKa of propane is 50, pKa of ethanol is 16, and then we have a phenol, this benzene ring with an OH on it. The Ka is 10 to the negative 10, and then toluene is the Ka is 10 to the negative 41. So remember, we're looking for the stronger acid. So for the first part problem, the pKa, the smaller the pKa, the stronger the acid. So that means the ethanol is the stronger acid. Now for the other problem, we're looking at Ka. So remember the larger the Ka, the more acidic the acid is. And so 10 to the negative 41 is a very, very small number. So 10 to the negative 10, although also a small number, is still larger, and therefore phenol is a stronger acid. Okay, and this is pretty much how you're going to walk through these problems. You're going to want to remember that the small pKa is the stronger acid. You can kind of correlate this to pH, right? Remember the pH of 1 is an acid, whereas a pH of like 10 or 11 is base. Okay, so smaller the pKa, stronger the acid. So strong acid also means that we have a weak conjugate base, and then a weak acid is going to be give us a stronger conjugate base. So this is important because it allows us to kind of predict whether or not reactions occur. And so let's try another problem, but rank the following compounds in order of increasing acidity, and then rank their conjugate base in order of increasing basicity. So when we're talking about acids, we can always translate that to a discussion of basicity, and that's exactly what this problem's doing. So again, if we have a strong acid, we have a weaker conjugate base, and then if we have a weak acid, we have a stronger conjugate base. So NH3, H2O, CH4, they have a pKa of 38, 15.7, and 50 respectively. Okay, so first what we want to do is rank them in order of increasing acidity. So water has the lowest pKa of this group, so it's the strongest acid, and NH3 is next in line, and CH4 is last. So this is increasing acidity. Now what we want to do is rank their conjugate bases in order of increasing basicity. So what we need to do is, or what we should do is, draw out their conjugate bases, because we need to know what their conjugate bases are. It's just an important task for us, but also realize that the trend is opposite. So if we have an increase in the increasing acidity of the acid is going to be the opposite trend for the increasing basicity of the conjugate bases. So what I mean by that is, if we draw out amide, hydroxide, and then this methide, this CH3 minus, those are all the conjugate bases of the acids given, right? And so the trend is now going to be opposite for the basicity of these particular molecules. So CH3 minus is the strongest base, while hydroxide is the weakest base. Again, notice that trend is opposite to the acids. And that's it for this one. Okay, have fun with the topic. It's really important, so get that practice in.